right, welcome to Chapter 8. This is Miss Fleming, and as always, we're going to start with lesson, whatever chapter it is, point 1. This is Introduction to Quadratic Functions. Okay, starting out, we are going to actually look at a set of functions called polynomial functions. And you should be really familiar with some of these at this point. We have a linear function as a polynomial function because it is x to the first power. We have a quadratic function that is polynomial because it's x to the second power. And we've looked at cubic functions a little bit. Cubic functions have x to the third power. So you can see the pattern here. Polynomial functions are going to increase by 1 power for the input variable, which is x. All right, so let's take a look at this where we talk about the first and second difference. Okay, to find the slope of a line, I'm going to subtract backwards. So I'm going back here. I actually don't have the pen on. Let's touch this and get the pen on. Going backwards. And bear with me because you know I'm not great at this. And we want the pen. All right, so subtracting backwards, -2 minus 1 is going to give me a -3. And I'm going to keep going right up here. 1 minus 4 is going to give me a -3. And 4 minus 7 is going to give me a -3. 7 minus 10, and 10 minus 13. So I found the slope by subtracting backwards, which is what we've been doing since chapter 2. We did this subtraction once. That's why it's called the first difference. This is a quadratic function, and you can't really recognize this from the table, but by the end of this lesson you'll be able to. But let me show you what a second difference looks like. And this is how I know it's quadratic, at least one of the methods. So 4 minus 1 is going to give me a 3. 1 minus 0 is going to give me 1. 0 minus 1 is a -1. 1 minus 4 is a -3. And 4 minus 9 is going to give me a -5. All right, at this point, there is a pattern forming, but that's not the one I want you to see. We just did a first difference, just like we did a first difference here. This is where we're really going to see the pattern. We're going to see it on the second difference. So I'm going to subtract backwards again. 3 minus 1 is 2. Okay? 1 minus -1. So 1 minus -1. I don't want to write all of these out, but I want you to see why. So a negative and negative is positive. That's how I'm going to get a 2 here. You're going to see the same thing that happens here. -1 minus -3 is the same thing as -1 plus 3. So that's a 2. You starting to see what's happening? So while quadratic functions don't have slopes, they have a second difference where I get the same number when I subtract the second time. All right, this is a cubic function. So this is x to the first power, x to the second power, which is x squared, cubic, x to the third power. So this is a lot of subtracting. 204 minus 113 is a 91. And I have to do enough that you can see, but you ought to be able to see what's going on. 113 minus 52 is a 61. I keep going up here. I'm going to get a different number every time, and I expect to. It's not linear. The only way I would get the same number every time is if it was linear and had a constant rate of change. All I want to do is get enough that I can move to my second difference and then my third difference. So -4 minus -11 is going to give me 7. Okay, so here's the second difference. 91 minus 61 is 30. 61 minus 37 is 24. 37 minus 19 is 18. And 19 minus 7 is 12. So I still don't have the same number, but now you can imagine first difference, second difference. I'm about to do the third difference, and most of you can actually see the difference between these numbers, 6. 30 minus 24 is 6. 24 minus 18 is 6. 18 minus 12 is 6. So we're going to focus on quadratics. Quadratics can be identified from a table by finding the second difference. I subtract back once, and then I subtract a second time with these numbers. If I get the same amount every time, it is a quadratic function. Let's clean this up. And here's the vocabulary for the chapter. Okay, first we're going to define what a quadratic function is. Basically, we are just going to give you all the equations. And this one is the one where you've got 4 different equations. You've got the parent function, which is the function you've seen before. We talked about this when we did transformations. The parent is the function in its most basic strict bound form. And so this is f of x is equal to x squared, or just y is equal to x squared. Okay, standard form. F of x is equal to ax squared plus bx plus c. The position of a, b, and c is incredibly important. A is the leading coefficient. It's in front of the x squared term. B is the one in the middle, and the c out here is just a constant with no variable. Now, when I have a quadratic function in standard form, it's really interesting because I get this little piece out here at the end. I have the y-intercept. It's right here. So just like all others, this is the y-intercept, and it's going to be in word problems, it's going to be the initial value. Okay, this is factored form. And out here, this a is a leading coefficient, but it is also a GCF. It is a greatest common factor. We did GCFs, I think, in chapter 3. So we're going to revisit those, and then we're going to do quadratic factoring. Now, the information that's in here, this was the y-intercept. We are going to have the x-intercepts in factored form. And it's not quite this straightforward. You can't just slap negative signs in front of them and make them. You'll notice that x-intercepts have y's that are 0. It's not quite that easy, but in general, the information containing the x-intercepts for the function are in here. And we haven't really cared about x-intercepts before, but in quadratic functions, the x-intercepts are pretty critical. The last form we're going to learn is vertex, or graphing form. F of x is equal to this a, which is the leading coefficient, x minus h to the second power plus k, or x minus h squared plus k. Okay, we've seen this before. We saw this in transformations. So this a in a transformation controlled whether we had a vertical reflection, a stretch, or compress. This, grouped in here with the x, controlled whether we have a horizontal shift, which left or right. And this k controls whether we have a vertical shift. And this vertex form gives us the vertex of the parabola. If you remember, the vertex is the highest. That's a really bad parabola. The highest or the lowest point on the graph is the vertex. And this negative in front of here doesn't mean the same as that. This negative means something else. We're not going to worry about it right now. But the vertex is the value of h and k, and that negative says opposite. Okay, we've done vertex before. We did vertex in chapter 1. The vertex is the highest lowest point on the graph. The vertex is an ordered pair. It's got 2 points. And we break this down, it's going to tell me what the maximum or minimum of the graph are. It's also going to tell me what the line or axis of symmetry is. And the axis of symmetry is an invisible line. It is going to be vertical, and it divides the parabola exactly in half. We'll look at that in a minute. We have something called twin points, which isn't really an official math term, but it's really, really incredibly useful thing to know. We're going to have these parabolas. They're U-shaped, and excluding the vertex, every point on a parabola has a twin point. It is the same distance from the axis of symmetry. These points have different x values, but the same value for y. So, I don't draw these well enough. I'm going to wait till we get to the graphs and then we'll look at it. So, never mind, ignore that. Last vocabulary word. The solutions for a quadratic. Okay, well, just like any other function, every point on the graph is going to be a solution. But quadratics have special solutions, and it's because quadratics appear in real life all the time. There's all kinds of things that are patterned after this parabola shape that happen in real life. So the solutions to a parabola can be real numbers or they can be non-real numbers. We're going to be concerned about the real numbers for algebra. We're going to leave non-real numbers for algebra 2. And solutions are often referred to as the roots or the zeros. And the roots or the zeros are called roots or zeros because they are the x-intercepts of the parabola. Now we're going to take a look at some parabolas and what the most important parts are. And we're going to look at a table and you're going to see the most important parts of the table. All right, I've got a table and I've got a graph, and they are both for this function. And that function is right here. F of x or y is equal to negative x squared minus 2x plus 8. Okay, this negative tells me that I have had a vertical reflection. And I also said that this was the y-intercept. So take a look at that. That's a vertical reflection. And this is in standard form. It's got an A, a B, and a C. So I've got a y-intercept right there that is at 0, 8. Okay, here's the graph of that function. I've got all of these markings on it to mark it up. We're going to find what is the critical information and a couple of other things that are equally important. Okay, right up here at the top, the highest or lowest point is the vertex. So if I label that, which it says name each part of the table and then find its value. So the vertex is an ordered pair, and this happens to be at -1, 9. Let's go over here and see. Okay, that's the y-axis right there. There's the x-axis. So if I go over 1, I'm on the left side. -1, -2, -3, and so on. So my x value is -1. If I come up here, that's 10 right there, so this is 9. So -1 and 9 is the vertex. Okay, this right here is that famous y-intercept. It's where it crosses the y-axis. And this is an ordered pair, and just like I told you, it's right there at the end of the function. It's at 0, 8. All right, right here I've got the two x-intercepts. It's where the graph crosses the x-axis. So both of these are x-intercepts. They're ordered pairs, and they have y values of 0. Y-intercept has an x value that's 0. X-intercepts have y's that are 0. So I've got one at -1, -2, -3, -4, and 0. And the other one is right here, so 1, 2, and 0. All right, we've covered the arrows except for this one. What do you think this is right here? It's the invisible vertical line that cuts this exactly into half. That is the line of symmetry or axis of symmetry. And it is, in shorthand, we pretty much say LOS from this point out. It's also the axis of symmetry. It's a vertical line. We saw this before already in chapter 1, so this isn't new. Vertical lines have equations that start with x's. The equation of the vertical line runs right here for -1. And look, it's right here. This is something I've pointed out before too. Okay? There's the line of symmetry. It's the exact same value. So if you can find the vertex, you know the line of symmetry is going to run through where x is equal to -1. Okay? Let's look at the other piece of the vertex, which is right here. We said this is the highest or lowest point of the graph. Okay? Right here at this green line. This is the highest point of the graph, and back in chapter 1, we learned the word for this. This is a maximum. If this graph had not had a vertical reflection, we would have had a minimum. And this is the y value of that vertex. So y is equal to a +9. Okay, couple of things why I put this down here at the bottom. Because we talked about twin points, and I want to show you about twin points and how they work. Okay, so every point on this graph, except for the vertex, has got a twin point. Right here, if I go, there's a line of symmetry, 1 over is that point, 1 over, it's got a twin point right there. Okay, right here, if I go over 2, 1, 2, I have a point right there. If I go over 1, 2, I have a point right there. Write down this line of symmetry, 1, 2, 3, 1, 2, 3. Okay, I'm going for good grid points, so I'm skipping points, but this works everywhere. Every point on this graph has a twin point. Okay, so now I'm down here, and I still have twin points. That one is 1, 2, 3, 4, and from that line of symmetry, 1, 2, 3, 4, there's the other twin point. So from the line of symmetry, every point on this side has a twin point on this side that is exactly the same distance from the line of symmetry. All right, this is the table that goes with this function. Clear up some room here. I need to find a way to adjust that so the eraser's bigger. All right, the first thing we're going to do when we have a table is we are going to look for things that have zeros in them. Okay, so right here, let's change colors. Right here, I've got something with a 0 in it. And I've got something with a 0 in it right here. And right here, I've got something with a 0 in it. Okay, why would I look for those? Because they're either x or y intercepts. Okay, this has an x value of -4 and y value of 0. So this is an x-intercept. This has a y value and x value of 0, so this is the y-intercept, which we already knew because we had the equation. And again, I've got an x that has got a number in it, a y that's 0, so that's an x-intercept. Now let's look and see how interesting and valuable the twin points can be. All right. The other definition of twin points said that they have different x values, but they have exactly the same y value. So let's look down here. I've got a y that's -7. There's a y that's -7. If I look over here, there's the twin points. They're right there. So here's a twin point to that point. That's a 0. That's its twin. That's a 5. That's its twin. 8, 8. That's its twin. What can we say about this one? Does this one have a twin? The only point on the parabola that doesn't have the twin is the vertex. No twin. I also want you to note something else about this. You see along here, we've gone from -7 to 0 to 5 to 8. From here to here, this graph is increasing. So it's going up. Then it hits 9 and it goes 8, 5, 0, 7. What's it doing there? It is decreasing. So the vertex is where this graph turns. If the graph went the other way, it would go from decreasing to increasing. But what happens, the big point here is the vertex is where that graph changed directions. All right, I've got one more point of interest, and it's where these red lines are. And this is pretty important. Right now, we've got all of the x and y intercepts. This is a really nice table. It shows all the values. If I put it in the calculator, they'd all appear in the table in the calculator because all of these x's are integers. Okay, well, what happens if my x-intercepts are not integers? Or my vertex is not an integer? Or this one's not an integer? This one always will be because that value is always 0. But the rest of them aren't necessarily going to be integers, so they're not going to show up in the table in the calculator. But what I can look for is this pattern. Okay, so what happened to the y's right here, and this is why I've got this red line. I went from a negative to a positive. Down here, same thing, I've got this red line. I went from a positive to the negative. And if I go look at my graph, what happened right there? Well, if I went from a negative to a positive, and a positive to a negative, I crossed the x-axis. Why would I care about that? Because it's going to tell me where my x-intercepts are. If they're not right there present in the table, I can actually estimate them really, really closely. So right there where that red line is, we cross the x-axis. And that was a lot of stuff, and it's a lot to worry about, but you're going to get enough practice to see it over and over. Okay, so let's go ahead and erase this. And go to the next page. All right, so here's the diagram that maps out, sorry about that, we always diagram every equation and label all the parts. So this is standard form of a quadratic. Remember, there's two other forms, and we also have the parent function. So standard form has got this idea where we have a leading coefficient, that is a. B always goes with the x term, and c is always a constant, and it is incredibly important that this is in this form, in this order, a, b, and c. And just like any other function, all functions have exactly the same two things in common. They all have an output, which is the y. This is the dependent variable, and it's the range. We've got two inputs this time, but they're still the independent variable in the domain. And this is the y-intercept, and if we had a word problem, this would be an initial value. We have one constraint: a cannot be equal to 0. If a was equal to 0, we wouldn't have an x squared term, and this would become a linear function. Okay, here's the parent, so if we get caught up in transformations again, this is the most basic parabola. Doesn't have any kind of transformations on it, and right here I've got a vertex of 0, 0. That looks like a 1. Let's make it look a little better. And in terms of stretch or compress, this goes over 1 and up 1, so there's no change. That's about all there is to say about that. Okay, let's look at our first graph. And this is example 1, so this is what's going to be in the practice. I put all the graphs in the practice, so you have to interpret them, but you don't have to draw any this time. So we are describing the graph. This is example 1. I want to fit as much as I can onto this as possible. Let's see if it'll let me do that. Nope, that's as big as I can go. So we're going to have to use our imagination a little bit. All right, this is the graph of the function y is equal to x squared plus 2x minus 3. So I've got a y-intercept. I already know, without even looking at the graph, I know I've got a y-intercept at 0, negative 3. And it's right there. Okay? My vertex is going to be the highest or lowest point. So if I look down here, and you're like, it doesn't look like a parabola, it looks like a check mark. Well, yeah, it does, because the graph kept going forever. In fact, the graph goes on here and never stops. There's an arrow here. And if I extend this out, at least in my imagination, there's the rest of the parabola. It goes on forever. Okay, so with that in mind, my vertex is my lowest point, and it's right here, and it is at -1, -4. All right, now, roots or zeros, those are the x-intercepts. In general, there are going to be two of these. Sometimes you have a condition called, ooh, I spelled that really awful. It says intercepts in there somewhere. In general, there are going to be two of them. Sometimes you have a condition where you've got one, and it's called multiplicity. You actually have two, but it's the same one 2 times. But we'll worry about that later. Okay, where do I cross the x-axis? I do here once, so that was pretty clear. So you're going, well, there is only one. Well, there's another one. But we can't see it. But we do know that this vertex has got an invisible vertical line that runs through it. Let's change colors. Here's my invisible vertical line that runs through, that is called my line of symmetry. And that line of symmetry says if I have a point over here, then I have a twin point exactly the same distance over here. So this is over 1, 2. Draw some lines there. So here's 1 that went to -2. If I go over 1 more, then I've got a point right here. And where is that point? It is at -3, 0. So you can put the idea of just twin points to work, and you can use the axis of symmetry to find them. So there's the other one. Okay, do we have a maximum or minimum? Well, it's the lowest point, so it is a minimum, so I'm going to circle that. Where is my minimum? It is not the entire vertex. My minimum is just this y value, the lowest point, and that y value right there is y is equal to -4, which happens to be right there. It's the y coordinate of the vertex. Okay, do I have an equation of a line of symmetry? Yes, I do. It runs right there. It's a vertical line, and it's also in the vertex. It is right here. It's x is equal to -1. So I found both x-intercepts, I found the y-intercept, I found the vertex. And from that, we got all of the information that we needed to know about maximums or minimums and line of symmetries. Okay, so let's answer the rest of these questions. Find an interval where the graph is increasing. Okay, well, let's look and see from left to right what this graph is doing. And I'm going to do this in green. Okay, from left to right. Coming down here, what is this graph doing? It's coming down. X values don't do anything to increase, but these y values are decreasing. So we are going to write an interval, and we're going to say, we can see from -3. So we're going to say where from -3, we're looking between -3 and -1. This graph is decreasing. We did this in chapter 1. So the y's are going to increase or decrease, but the interval is going to be instated in terms of x values. We started at -3, which is right here. We could have picked another number, but I just picked what we could see. And from here, that's where we are decreasing. Oh, wait a minute, increasing. I just did this backwards. This one goes here. I'm not starting over. I'm not editing the video. If you were in class, you'd have to suffer with this. This is the one where it's decreasing. Now we're going to go find the one where it increases. So let's do this color. Sorry about that. Okay. All right. While I'm erasing, you're looking at the graph. Okay, so you could obviously tell at this point, and you're all laughing because I made a mistake. That's what it's like in class too. So, all right. This one is decreasing, so we put it in the right place. This side is increasing. It's going up. My y values are going from -4 to +3, at least for this space. So where can we put that? We know it's over here, but we're going to go ahead and pick an interval that we can see. So from here, and we're going to say the -1 again. So between -1 and 1, between these two x values, this graph is increasing. Wow, that was great. Okay, now let's erase some of this because it got really junked up. And we're going to find the domain of range, which you should be old pros at, that you should probably be able to do with your eyes closed. Okay, so the domain is going to be all possible values for x. We start on the right side and we move to the left. I just said that backwards. We start on the left and move to the right. Let's erase this. And up here we have our infinity symbols, because this graph goes on forever. So from left to right, now that I've got that straightened out, we started at infinity, and we're talking about the domain, and we are going to end at infinity. We can't write domain with infinity symbols. We have to get rid of these. If I have 1 here, 1 here, then my x values are equal to all real numbers. Okay, on my range, on the other hand, starts at the bottom, moves up. So starting down here, the first value for my range is -4. And going on up here, it goes to infinity. And I can't keep that infinity, so I get rid of that. I have to start my range with the y, so this entire thing gets reversed, including that sign. So my range is y is greater than -4. And because this is a solid line, that is actually a greater than or equal to. Solid line is just like an inbuilt dot. All right, describe the transformations of the parent. So what do we think happened? Well, I know that my vertex for my parent is right here, and it goes up like this. So my vertex originally was at 0, 0. And my vertex right now is at -1 and -4. So I've got to have both a horizontal shift and a vertical shift. I have not had a vertical reflection, and this is still 1 and 1, and this is still 1 and 1, so I haven't had to stretch or compress. So what have I done? Well, I have gone over 1 over here, because there's that, and there's my -1 of my vertex. So I had a horizontal shift, and we went left 1. And then I had a vertical shift, and if I went over here 1, I went 1, 2, 3, 4, which is right there. I had a vertical shift down 4. All right, the graph is symmetric to the line of symmetry. I can fold this in half right down there, and this is a mirror image of that side. We know that because it has twin points. But does it also have even or odd symmetry? Okay, well, if I had even symmetry, then this graph would reflect across the y-axis. And it's pretty junked up at this point. But let's clean it up a little bit so you can see. Right now, the y-axis is right here. The line of symmetry is here, so no, it does not reflect across the y-axis. Okay, and for odd symmetry, it would reflect across the diagonals. So the diagonals run this way and this way. So if I look here, is this part of the graph reflected down here? No, it is not. And up here, I have nothing. And down here, I've got this piece. So those are not reflected. So it does not have even or odd symmetry. So the answer to here is no. Or neither, either one. Okay, let's erase this. Now we're going to learn another one of those really useful little tiny formulas. And this is a formula to find the vertex given the equation, and it only works if the equation is in standard form. So, let's talk about standard form again. So I've got ax squared plus bx plus c. And it has to be in standard form because that is A and that is B, and it only is A and B from standard form. And this is the formula. It says the vertex, which is an ordered pair, the x value is going to be negative B divided by 2 times A. And once I have that x value, if I plug it into the function, I'll get the y value that goes with it. So this is A, this is B, and this is C. So my x-coordinate, remember, I'm looking for a vertex. I'm looking for an ordered pair. So the x-coordinate of the vertex is going to be x is equal to, okay, that negative is part of the formula. So I'm going to substitute into parentheses so I can keep my negative straight. This b is a negative 2. And I'm going to use parentheses on the bottom because I want to keep my multiplication. So I've got 2 times a. And a happens to be 0.5. So that is going to give me positive 2 over 1 or just 2. And you run that through your calculator and you work that out. So I take that, that's an x value, and I'm going to plug it in here now and get a y. So y is going to be equal to 0.5 times 2 squared minus 2 times, minus that 2, and this is the 2 I'm substituting, minus 4. And you're going to run that through your calculator exactly the way it appears, including all the parentheses, and what you're going to get out is a y is equal to negative 6. So up here I've got an x of 2 and a y of negative 6, and that is my vertex. Okay, now I've got an A. I do not have a B, but I have a C. Okay, so let's go ahead and put in a value for B. And if you can do this in your head, that's fine, but I think it makes more sense to write it out. If I am missing a B term, then my B term is going to be a 0. It's the only thing it can be. Oh, that's an X. Excuse me. The B is 0. That's an X. Plus 6. All right, so what does that do? It gives me an A of negative 3, a B of 0, and a C that is 6. So I plug that into my formula, and x is equal to negative 0 over 2 times, which is right there, and A is negative 3. Well, this is my favorite kind because anything, I can divide anything into 0. This is fine. That tells me my vertex is going to be 0. Okay? So let's put this one right here. Right now we know that x is 0. And if I plug that 0 in, I've got y is equal to negative 3 times 0 squared plus 6. Well, 0 squared is 0. Negative 3 times 0 is 0. So this is going to give me a y of 6. So the vertex for this is 0, 6. Okay, now we're going to look at a couple of interesting sort of word problems. One of them we're going to use the parabola to describe what's going on. I think you're going to find it really interesting. And it's going to be helpful when we actually do word problems because they'll help you visualize what's going on. All right, so I have a parabola here that is in real life or real life application. How much can I get on here? Pretty much all of it. Okay. Here's the situation. I have a rocket that was launched into the air from a platform, and it's going to follow this path of this parabola. Goes up, comes down. You can see why so many things are modeled after parabolas and quadratics, because a whole lot of things go up and down. In fact, they're called projectiles. So, define the variables and label the x and y axis. Well, let's finish reading it. The rocket is launched from a platform and follows the path shown on the right. Its height is shown as a function of meters per second. Okay, so what that tells me is I've got a rate here. It's not a rate of change that's constant because this isn't linear, but this does tell me what I'm looking at. I've got the x-axis is along here, specifically right here. So this is going to be seconds. And right here, it's following a height. And I've got to write sideways. That ought to be interesting. That's the height, and it is still in meters. All right, so the variables, x is going to be equal to the number of seconds. So we shoot it off. It's in the air for some amount of time. And while it's in the air, it reaches a certain height, and whatever that height is, it's in meters. So this is height in meters. Put it this way, so it's sideways is interesting. All right, the domain is all possible values for x. So let's look at this. Here's 0. This is where it got fired off. Here's the first second it's in the air. There's this, oh no, these are by 10. So this is 2, 4, 6, 8. Sorry about that. 2, 4, 6, 8. This is 0. This is -2. So do you think it would be reasonable for it to have a domain that includes a -2? I don't. I think my first entry in my domain is going to start right here at 0. And where's my last entry for my domain? Well, this is where this rocket is going to hit the ground. I'm not going to have anything down here. So I think that's going to be my last entry for the domain. That was 10. This is 12. So I think I'm going to start at 0 and go to 14 seconds. So the domain is 0 and includes that. So from 0 to 14 seconds, that is my domain. Get rid of those. Okay, let's see what kind of grid or what kind of scale we've got for our meters. All right, let's see, that's 20, so it's 5, 10, 15, 20. The range is all possible values for y. Okay, so bottom to top. Right here is where the rocket hit the ground. Now you're going to be tempted to go up here, but right there is not going to be my first value for y. My first y value is right here. Even though that's right up on the graph, the first value for y is right there at 0. That's the lowest point. And I keep going up here, and this is going to be my last value for y. It's a solid line. And these are both solid lines. Okay, so we said that's 65 because the scale was in 5s. What was the height of the launching platform? That's where we started from. This is our initial value. If it's my initial value, then it is my y-intercept. So where is the y-intercept? platform is right here. So the viable path of this, or the path that this really took, it started right here, where it left the platform. It went up, gravity grabbed hold of it, and it came down, and it hit the ground right there. And that's the only part of this graph that actually has any meaning. Anything else on this graph is just fluff. That's the path of the rocket. So, what was the height of the launching platform? Oh, I wrote that terrible. The initial value, or the y-intercept, this is by 5, so that's 25, it is 30. And we're in meters, so it's 30 meters. How long did it take the rocket to reach the ground? Okay, long, how long is time? So this time I don't care about height in meters, I don't care about time in seconds. How long did it take it to reach the ground? It left right there at 0, and it came down after 14 seconds. How high did the rocket go? Well, its maximum height is right here. And that maximum height was 65 feet. How long did it take the rocket to reach that point? So how many seconds did it take it to go from this platform up to there? That's 2 seconds, 4 seconds, and it looks like that's 6 seconds. How high was the rocket after 2 seconds? Here's 2 seconds. So I'm going to come up here and find the height in meters, and it looks like I'm going to have to guess a little bit. That's 45. It's not quite 50. I'm going to say roughly 48 feet. 48 meters, excuse me. How many seconds did it take the rocket to reach the same height when it began to descend? So right now I'm looking for the twin point. Same height when it began to descend. So this is what's going up, it's ascending. This is where it's going down, it's descending. And so right there, same height when it began to descend. So that was 2 seconds to get to that height. Wait a minute, it was 6 seconds to get there. And to reach that height on the descent, I'm double checking because I want to make sure that I don't give you an answer that's different than everybody else's. That is going to be 10 seconds. So at 2 seconds we reached approximately that height. And after we've gone a total of 10 seconds, we were at its twin point. And there is one more question. No, that is the last question. Good. I did get it all to fit on the screen. Okay, we've got one more example, though. This is a 2-day lesson, so the videos are long. So hang in with me. I've got one more. This time I'm going to use that vertex formula in a real-world situation. All right, example 4. And we have the daily temperature in degrees Fahrenheit in Death Valley in 2003. So this was in 2003. Can be modeled by the temperature, and it looks like D is going to be days, is equal to negative 0.0018 D squared plus 0.657 D plus 50.95. What was the maximum temperature to the nearest degree? On what day in 2003 was the temperature reached? Okay, so we've got a big T that's going to be temperature. We've got a little d that's going to be days. We're inputting the d's to get the output of temperature. So our independent variable is going to be D. And it represents the number of days. Our dependent variable is going to be that uppercase T, and that is temperature. And that temperature is in degrees Fahrenheit, but we aren't going to worry about that right now, other than put a degree symbol there so we're remembering the units. All right, find the vertex using the formula. Okay, the vertex is x is equal to negative b divided by 2a. So let's go ahead and make sure we've got an a, b, and a c. Okay, this would be our x term, this x squared term. This would be our x term, and this is going to be the constant by itself. So this is A, this is B, and this is C. And my formula says that x is going to be equal to negative b. The negative's in the formula, so 0.657 and that is divided by 2 times negative 0.0018, and that's going to give me the x coordinate of the vertex. And if I run that through my calculator, it is equal to 182.5. Okay, to get the y coordinate of the vertex, this is x, I'm going to plug that in. And this is going to be, wow, and as bad as I write, this is going to be really ugly. Okay, y is equal to, I've got negative 0.0018, and all of this, 182.5, this is squared, plus 0.657 times 182.5, and then I just have the constant at the end, which is 50.95. And I'm not going to try and do anything fancy here. I've used parentheses, so I've got all my signs preserved. I've got all of my multiplication preserved, so you run that, all of that right through your calculator, and that is going to give me a y is equal to, all right, 110, left a 1 off here, she's got millions of decimal places. I'm going to round this to the 10th, so I'm going to use that. All right, so what does that tell me? Okay, I'm going to break this down and write this vertex because it's going to be really interesting, and you're going to see how we take this apart. I've got an ordered pair that's a vertex. My x coordinate is 182.5. My y coordinate of this vertex is 110.9. Okay, now I'm going to go look at my variables. X was days. And y was temperature in degrees. And I'm just going to put temp in degrees. So now I understand what I have. Now I'm going to go answer the questions. What was the maximum temperature to the nearest degree? All right, well, there's the temperature. We could have even rounded it more. It was 111 degrees because we round up. On what day in 2003 was the temperature reached? It was reached on the 182.5 day. And I bet you could find an application on the internet. We have 365 days in a year. This is going to be about halfway through the year, so this is going to be sometime in July, I would imagine. And if it's 0.5, it's going to be noon. If you find one of those applications on the internet, put in the day and it will give you the day of the year. But that's not the point. The point is, we had an equation, we found the A, B, and C, we plugged it into the formula, and we didn't worry about anything until we got the vertex. The vertex itself is right here with the x value we found and the y value. Now we had to understand the variables. What we were putting in here was D, which is days. What we were getting out was T, which is temperature in degrees. Now that I knew both those pieces, I could answer this question. This is D, it was days. On what day? Got the days. This was temperature. What was the maximum temperature? 111 degrees. All right, that is the end of this lesson. It was long. It's a 2-day lesson, so you can always pause the videos and resume and break the practice up in 2 days. All right, I will see you next time. And no, my handwriting probably won't get any better. So that's it. Over and out. Bye.